In lesson 6 of cycle 3, we're going to move on to rational functions. And just like everything we do with cycle 3, we're going to be working with the equations. We're going to be sketching things by hand. Of course, we can still use Desmos to check our answers, but the whole point of this cycle, again, is to do sketching from what we know about the characteristics, that what we can understand from the characteristics. So remember that a rational function is one that can be expressed as p at x over q at x, where p at x and q at x are each individually polynomial functions. Also remember that q at x can't equal 0. If q at x were to equal 0, then we'd have a division by 0 error. So wherever q at x does equal 0, we're going to get an asymptote. So let's start off, just a reminder what vertical asymptotes are. They're imaginary lines that a graph approaches but never touches. They occur when the denominator equals 0. So what we do is we find the values of the denominator, or the values of the variable that will make the denominator 0 if we're looking to find the vertical asymptotes. Zeros, or x-intercepts, occur where the numerator equals 0, because we want to find where y, the output, f at x, equals 0. And since it's a fraction, it stands to reason that our fraction is going to equal 0 whenever the numerator equals 0. Since p at x is the numerator, we just have to set the numerator equal to 0 and solve that. It doesn't say anything here about y-intercepts, but remember we can get y-intercepts easily by putting 0 in for x into the function and just seeing what's left over. And for horizontal asymptotes, remember those are imaginary lines that the graph can cross. They can cross it. But if we look at the end behavior, that's what the horizontal asymptote is, what the end behavior is tending towards. Now, in this lesson, we're going to look at 3 different possible scenarios, and they all depend on the relative degree of the numerator compared to the denominator. So, if the numerator is a higher degree than the denominator, the first case here, then we're always going to have a horizontal asymptote on the x-axis where y equals 0. So for example, let's look at this function here. We've got x plus 3, which is a linear numerator. X plus 3 on its own is linear. On the bottom, we've got a quadratic. We've got x squared. So on its own, x squared would be a quadratic. So in this case, we're always going to have the horizontal asymptote be the x-axis. In other words, the output, f at x, is always going to get closer and closer to 0. And there's a good reason, logical reason for this. Imagine what happens at the end behavior. So end behavior is when x is really big or really small. So if x, let's pick a big number. If I had x is, well, let's pick 100. I mean, that's not, we can go a lot bigger than that, but let's just pick 100. If I pick an x value of 100, then what I'm going to get is 103 over 100 squared, which is 10,000. And that's approximately equal to 0. Well, it's approximately equal to, I guess, 1/1000th to be more precise. But you get the idea. It's a small number. If I was to go farther, well, say I picked an x value of 1,000, well, the difference between the numerator and the denominator is going to become even larger. We'd end up with 1,003 in the numerator, and we'd have 1,000 squared, which is 1,000,000 on the denominator. So the farther out to the right we go, we're actually getting smaller and smaller output values, right? So that's our explanation for why we have f at x equals 0 as our horizontal asymptote whenever the numerator is a lower degree than the denominator. When they're the same degree, using the same logic, we can sort of predict what's going to happen. But here's the rule first. H at A, the horizontal, HA, horizontal asymptote will be the ratio of the leading coefficients. So again, let's try this little thought experiment again. Let's pick a big number here. If I was to pick f at 100 again for this one, well, 100 squared, we saw, is 10,000. And if I multiply that by 4, I get 40,000. That's a big number. But we're getting big numbers on the bottom as well. We're going to have 2 times 10,000, which is 20,000, minus 100, so 19,900, plus 7, so 19,907. Just did that in my head, so forgive me if I made a little mistake. But it doesn't matter. What you can see is when I divide it out, that's approximately equal to 2, which is really just the same as if I took the ratio of the numerator and the denominator. It's because the x squared terms get so much bigger, so much faster than either the x term or the constant term, which doesn't move at all, that it's like those other terms don't even matter. So we can just forget about them, and then, obviously whatever the x values are, they're going to cancel out. So as we get closer and closer to 0, as we get farther and farther out to its infinity, we're going to get closer and closer to 4 over 2 in this case. It's always just the ratio of the numerator to the denominator. And the last possible scenario is if we have a higher degree in the numerator than in the denominator. In that case, we're not going to have a horizontal asymptote at all. However, there's another subcase of this, and that would be if the numerator is exactly 1 degree higher than the denominator, what we're going to have is something called an oblique asymptote, which we'll talk about in the next lesson. But really, what it means is an oblique asymptote is a slanted line. So instead of a horizontal line that will give us our end behavior, we're going to have a line that's on an angle. Now, this example here doesn't have the numerator 1 degree higher than the denominator, so this wouldn't be a case for an oblique asymptote, but neither would it be a case for a horizontal asymptote. We've got a degree 3 in the numerator and a degree 1 in the denominator. They are going to be no horizontal asymptote, no oblique asymptote, and so, but we recognize it that way. Okay, so this is quickly sketch, and hopefully you can see that we can do it quickly when we understand what to look for. We got 4 examples. So we want to sketch f at x equals x plus 1 over x squared minus 2x minus 3. So the first thing we should always do if it's not factored is factor it. So we need to factor the bottom. 2 things that multiply to give negative 3 and add to give negative 2 are negative 3 and positive 1. So those are my factors. And so now we start to think about the different characteristics that we just talked about: vertical asymptote, horizontal asymptote, x-intercepts, y-intercepts, and if we put that together, we can probably get a pretty good idea of what the graph's going to look like. There's one extra twist for this one, though. You may remember that when you have the same factor in the numerator and the denominator, we can reduce this, right? This reduces to just 1 over x minus 3. But I still have these restrictions of x can't equal 3 and x can't equal negative 1 from looking at the denominator here. All right, so the x can't equal 3 is easy. That's just a vertical asymptote. So vertical asymptote, so if x can't equal 3, that just means we have a vertical asymptote at x equals 3. But x can't also can't equal negative 1, and we've seen before that's not an asymptote, that's a hole. So we're going to have a hole at x equals negative 1. So it's not something that the graph's going to get closer and closer to, sort of shooting up or down like vertical asymptotes normally do. It's just going to be the graph's going to go along, and it's going to approach this hole, and at the hole it'll be undefined, but otherwise it's just the graph's just going to carry on doing what it does. So we'll graph it and see in a minute. But we still want to think about what's the x-intercept. And remember, that's going to occur when f at x equals 0, which is going to occur when the numerator equals 0. So the numerator is x plus 1. X plus 1 will equal 0 when x equals negative 1. Therefore, we have an x-intercept at... Sorry, my bad. I just totally forgot I was talking about the hole. We would have an x-intercept at negative 1, but we've canceled that out. So there's no x-intercept. I had a complete brain blockage for a second there. We do have, however, a horizontal asymptote, and we'll see why there's no x-intercept, because if we look at the degree of the original polynomial, we have degree 1 over degree 2. That was a case, the first case we saw, where the horizontal asymptote will always be the x-axis, y equals 0. So y equals 0 is my horizontal asymptote, and we could have an x-intercept, as I've said before. It is possible to cross the horizontal asymptotes, but in this case it's not going to. There's nothing, once we've reduced the fraction by canceling out the x plus 1 on the top and the bottom, there's nothing left to give us a horizontal asymptote if we're just looking, or an x-intercept. If we just look at this part here, there's no way that I could make that fraction I just circled ever equal 0, so there's no x-intercept. Finally, y-intercept. That comes from letting x equal 0. If I put 0 into this equation, and again, I might as well just look at the simplified version because I'm going to get the same results either way. If I put 0 in for x, I get that y equals 1/3, right? So, negative 1/3. So, that's some good information that's going to help us sketch our graph. So maybe I'll just use green for my asymptotes today. So vertical asymptote at 3. I'll just show that with a dotted line. No x-intercept. I'm going to skip the whole for now. Horizontal asymptote is the x-axis. Different dotted line. Y-intercept at y equals negative 1/3. So I'll put that here. There's negative 1/3. I can probably guess what the graph's going to look like from here. It's going to be down in the bottom left and top right corners of the way this is broken up. But if I want to be sure, then what I can do is I can also do what's called a test point. So I can just pick an x value, throw it into the function, and just see. So if I look at x equals 4, I'm kind of curious at what's happening when x equals 4, just to make sure that I'm on the right track with what I'm predicting. So I'll just find out what f at 4 equals. And again, I can use the simplified version, the 1 over x minus 3. And when it turns out that when x equals 4, y equals 1. So that gives me a point that I can put on my graph, again, to help round out my picture. Let's do that in red, though. All right, so putting it all together, vertical asymptote, we're going to get closer and closer to that. Horizontal asymptote, we're going to come down, but we're not going to cross it in this case. Starting with the point I have for the y-intercept, then I would expect that the graph's going to go something like this. And it's not perfect here, but it's close, right? We're just drawing a sketch. Now I'm going to expect to get closer and closer to the x-axis from below, but remember we have a hole at negative 1, so I'll represent that with an open circle and sketch it in like this, and there's my function. And I can always check it on Desmos later if I'm curious, but that fits all the criteria that I had. So that's how we can sketch things using the information we have. So let's do the next one, x plus 1 over x plus 2. Okay? Well, definitely not a hole in this case because nothing's canceling out. Vertical asymptote, yeah, that's going to happen where the denominator equals 0. And so that's going to be when x equals negative 2. Horizontal asymptote occurs. Now remember, this is a case we got a degree 1 polynomial on top, a degree 1 on the bottom. They're the same degree. So we saw that in that case, we take the ratio of the leading coefficients, which are both seem to be 1 in each of these cases. So 1 over 1 is our ratio. So we're going to expect a horizontal asymptote at 1 over 1 or just 1. So it's not the x-axis this time, it's y equals 1. We have we're going to have an x-intercept in this case where the denominator sorry, where the numerator equals 0. So if I let x plus 1 equal 0, then my x-intercept is going to be at -1. My y-intercept is going to occur where when I let x equal 0, what am I left with? I'm left with a half, just 1 over 2. So again, we can draw our sketch. Asymptotes first. Remember, horizontal one's at y equals 1. We've got x-intercept at -1. We've got y-intercept at positive 1/2. So with these 2 points, it seems to me pretty clear that the graph is going to look like this. And I think I can predict that the other part of the graph is going to be up in the top left. But if I want to really be sure, then of course I could pick an x value that might be down there. So maybe I'd pick -3 for an x value just to do a test point. Then I'd get -3 plus 1 over -3 plus 2. And I would end up with -2 over -1, which is positive 2. So I'd have the point -3, 2. I'd have this point, and yes, that is what I was expecting. I think it's safe to draw the rest of the graph. So it doesn't take long, right? Let's try another one. Here we've got a degree 2 quadratic over degree 3 cubic. So, again, we're just looking for the same types of things. Start with the vertical asymptote. Those are often the easiest. So, we're going to have a few. We're going to have x equals 3, x equals -5, and pay close attention to this one because people often neglect our little friend here because he's not in brackets, but that also is a factor. X is also a factor. If x equals 0, we're going to have division by 0. So we actually have 3 vertical asymptotes in this case. Horizontal asymptote, well, we've got degree 2 over degree 3. We've got a lower degree on top than on the bottom. That's always going to give us the x-axis as our horizontal asymptote. X-intercepts. I just did it again. Sorry, I'm going too fast. I just went back and suddenly realized I hadn't considered holes again. So we do have a hole, so I'm going to have to backtrack on something I just said. This x plus 5 and this x plus 5 cancel out. We don't have to change much, but if they cancel out, that means that I do need to get rid of this is no longer a vertical asymptote. So my apologies there, but it's not going to mess us up too much. I just have to erase that, and then we'll just indicate that we do have a hole at x equals -5. Now, x-intercepts, there is going to be an x-intercept, not at -5, since we got a hole there, but we will have an x-intercept at 4. And y-intercept occurs when we let x equal 0, but if I let x equal 0, I'm going to have a division by 0 error, again because of this x here. That's why we have a vertical asymptote at x equals 0. What that means is there is no y-intercept. Because there's a vertical asymptote there, then we can't have a vertical asymptote on the y-axis and have a y-intercept. So there's none. Okay, so let's sketch what we've got so far. So vertical asymptote 3, vertical asymptote y-axis, horizontal asymptote x-axis. That was supposed to be on the x-axis. I'm going to fix that. That's better. So 2 vertical asymptotes, 1 horizontal asymptote, 1 x-intercept at x equals 4. And really that's all that we have so far. We have a hole at -5, but again, we we can't really tell exactly where that hole is on the y scale for now. So this is a case where we probably are going to want to do a few test values. So maybe we'd pick -1 just to see what happens there. If I put -1 in for x, then I'm going to end up with -20/16, which is about -1.25. So I'll have a point at -1 and -1.25, so about here. Okay. So now, even with that point, it's probably even enough to let me predict, well, it's going to go down like this, and it's going to come back towards the x-axis here. Whoop, but we have a hole, right? So I'll draw my open circle, and then I'll keep going. Okay, let's predict what's going to happen. We got an actual x-intercept at x equals 4. So how does that play out? Let's try another value. Maybe let's try x equals 5, just to see what's going on there. And if I put 5 in, I'll get -18/-12, which reduces to 1.5. Okay. So I do get an x value there at 1.5. Sorry, that was for f equals 1. Wrong value there. When I put 1 in, I get 1.5. So I get x. Let's do that one instead. I just had a couple points pre-made to save us time, and I did the wrong one. So when x equals 1, we get 1.5. So, okay, we got something like this going on. If it can't cross the x-axis, then what's got to happen is it's got to come down, it's got to turn around, and it's got to go back up, right? So something like that is happening. And then if I do f at 5, what I had was that we get 10/100, which equals 1/10, or 0.1. So what we have is a very slightly above the x-axis point. Still might be a bit confusing to us. What's going on? Like, we may not see what's happening. So let's try one more. Let's try f at 10. Now, I didn't pre-calculate that one, so let's just calculate it now. Grab my calculator so I don't make any silly mistakes. So if I put 10 in for x, I get 15 times 6. So I get 90 over 10 times 7 times 15, 1050. Well, 90 divided by 1050 is 0.009, let's round it to. So still very small number. So in fact, it's going back down towards the x-axis. It was actually higher when x equals 5 than when x equals 10. So we do have the end behavior. I think if I was to put bigger and bigger numbers in, we're going to keep getting closer and closer to the x-axis. So I think we can predict it's going to look like this. It is going to come up and cross the x-axis, but it's not going to go very high, and then it's going to start moving back again down towards the x-axis. Again, don't forget, rational functions can cross horizontal asymptotes. The horizontal asymptotes just give us the end behavior, not the overall. They're not hard and fast rules that we can't cross. Okay, last one. I'm going to just get rid of this because it's in my way for my last example. What we have here is a degree 3 over a degree 5 when I multiply all the factors together or count up all the order of the different factors. So we definitely got a higher degree on the bottom. So let's talk about the horizontal asymptote first, since that should be on our minds. It means that, again, we do have one, and it's going to be a y equals 0. Vertical asymptote, there's no holes. All right, I pre-checked this time. So the vertical asymptote is going to occur where the denominator equals 0, x equals 2, and x equals 0. So again, we got 2 of them. X-intercepts. So whatever's going to make the denominator equal 0. So for the first bracket, we have a 0 at x equals -5. For the second bracket, we have a 0 at x equals +4. So you put the two together, and you got 2 places that it crosses the x-axis. Again, you can see that we've got a vertical asymptote on the y-axis, so we know we're not going to have a y-intercept. We can just skip that part. Okay, so we can sketch our graph, start with our asymptotes, -5. Sorry, that was an x-intercept. So vertical asymptote at +2 and at 0, and a horizontal asymptote on the x-axis, and x-intercept at -5 and +4. Okay, again, that's good. It's not enough to give us to really be able to draw the graph. So we really need some test points. So again, just pick some. Let's start with maybe +1, an x value of +1. When I do that, I get 54 over -1, which equals -54. So that's way down off of our graph. But what we've seen is if we have a point way down here, and we know it's not going to cross the x-axis, and we know that because there's no x-intercepts in this range here, so it can't possibly cross the x-axis, it must be facing down and away. So let's say that this is the point 1, -54, and I know that that's not really matching the scale, but I don't have enough room to actually put it to scale way down at -54 on the y-axis. So we're going to have that one chunk there. Let's try another test point. How about at f equals 3? Then I'd have 8 over 81, which is about approximately equal to 0.1. So we have something that is just above the x-axis here. So if we know we got one that's just above the x-axis, it must be coming down again from the top. I know this because otherwise there'd be another x-intercept somewhere around here, right? But there isn't. So it must be coming downwards from the top, hits this, crosses here, and again we know that the end behavior is the x-axis. So it's got to cross, and then it's going to start going back towards the x-axis again because of that horizontal asymptote. So we know this. You know, we can use logic like a detective to put these things together. Last thing, let's get one other point so we can see what's happening. So what if we were to predict or pick -1 for an x value? If we do that, we get 100 over -3. So that's approximately equal to -33 1/3. So at -1, we got a point that's way down. It's off the graph, but it's coming up. So we know already that the graph is coming up this way, doing something like this. It's going to cross the x-axis, but again, we know the end behavior out on this end of the graph is getting closer to the x-axis, so it has to turn back towards it. And, you know, we could do another test point if you want to confirm that for yourself. If you put -10 in for x, see what you get. That should confirm what we were just talking about. So that's a variety of different rational functions, just to give you an idea of what we want to think about while we're trying to graph them by hand.